Can I start now?
Yes.
Okay. So very good evening to all of you. So welcome to the 10th lecture. So 10th lecture, this is a 12 lecture course on solid state NMR spectroscopy, basic aspects of solid state NMR spectroscopy. We have discussed many points like what is magic angle spinning, what is cross polarization. Then last class we discussed how to use two-dimensional NMR called double quantum NMR to interpret structure of phosphate glasses for a better understanding. Because one-dimensional NMR is also good, but it gives certain information which are hidden. Some informations are hidden in the NMR spectrum which we cannot get by doing only NMR. Only NMR. Why this is not moving? Okay. So we have discussed in this aspect how to get some information from two-dimensional NMR spectra. So welcome to this 10th lecture. So today also we will discuss something similar to that only. How this 2D NMR can be used to get some more information regarding the structural aspects of glasses. So if you remember last class, we told that dipole-dipole interaction is an important aspect for this type of two-dimensional NMR or this DQ. DQ is nothing but double quantum. Something I forgot to tell you last class is that double quantum, single quantum, and there is something called zero quantum. You see here zero quantum, there is no change in the quantum. Alpha, beta, same model. So there is no change in quantum, so that is why we call it a zero quantum experiment, which we will not discuss. Basically, we are now discussing about the double quantum experiment. We have a particular pulse sequence. We will not go very much into that pulse sequence. So the main purpose of this pulse sequence is that we should, by using a suitable technique or suitable pulse sequence, we should bring this dipole-dipole coupling. Then only we can have a good communication between the structural units. So in this class, I told there's a good communication between Q1 and Q2 units. Q1 and Q2 units, and if you see Q1 communication is very less. Q2 to Q1 is relatively less. That also we will explain because it's a big chain. So NT groups can communicate with the other groups also. So this we have explained, discussed in the last class. So this spectrum very clearly shows there's a dipole-dipole interaction and there's a communication between the Q1 and Q2 structure, which that information we will not get from just by recording one-dimensional NMR. So for refreshing your memory, so what we have told in last class is that dominant DQ peak in double quantum peak involving Q1 is the cross peak 1-2. You see the cross peak 1-2 is the dominant peak, indicating that there is a good magnetic exchange between Q1 and Q2. And Q2, the auto peak, among the auto cube, if you see auto peaks or the diagonal peaks, the Q2 peak is more dominating. So Q2 peak is more dominating means Q2 interactions are taking place significantly. So that is possible if you have a very long chain, then definitely the Q2 interaction will be long. For the weak Q1 diagonal peak, the weak dipolar coupling is there because NT groups are always separated away. So their distance will be very large, and once the distance is very large, dipole-dipole interaction is inversely proportional to the cube of or distance between the NT groups. So obviously you will not see much interaction between the Q1 group, and in between sodium ions are there, which also prevent the communication. Now let us continue with that. What information we can get? One information which we can get is that in the glass we have a Q2 long chain Q2 structural units. You see here Q2 marked by N. N can be a large number. And this is nothing but a linear chain, linear chain. This is what I have written here, linear chain. Like that, many linear chains can exist in the glass. And if you see Q1 is here, this Q1 is here, this Q1 is here, and they are well separated. So communication become problematic, and so you may not see much Q1, Q1, diagonal peak or the diagonal peak. Whereas Q1, Q2 can be very clearly seen here. Similarly, the other chain also can be there. There also Q1 can interact with the Q2. So that type of interactions can be there. This is one possibility. So, and as the most probable possibility, because if you see here now from 1D NMR, you can calculate how much Q1 is there and how much Q2 is there. This is just by doing a Gaussian fitting. you can calculate what is Q1, relative concentration of Q1, and what is relative concentration of Q2. So from that we can get an idea regarding how many Q2 can be there, how many Q1 can be there. So you can also predict how many long chains will be there with Q1 structural unit and Q2 structural units. The broadness we have explained in the last class, correct? Na? It's because something to do with the rigidity. Probably we will not explain it furthermore. And if you see the chemical shift value also, if you see here, na, see the 2-1, the peak corresponding to 2-1, which is merged in the 1D spectrum, is slightly, you see here, slightly having a positive chemical shift. You see here 2-1, 2-1, here you see here. This is the peak corresponding to 2-1, means to Q2 to Q1 transition, and this is having a slightly lower chemical shift compared to the main Q2. You see main Q2 is coming here around 5 to 6 ppm or 2 3 ppm less for the Q2 to Q1. So that indicates that this is something to do with the end groups. The moment if you say a big chain, if you come towards the end groups, for example Q2, when it comes to the end groups, then Q2 to Q1 transition is more probable. In addition to that, there is a bond order increases in Q2 because they are coming towards more and more closer to the ionic side. So chemical shift slightly increases. So this is also can be explained by this 2D NMR. It's a very minor thing or maybe one of the additional information given by this double quantum NMR. Because if the Q2 units are the middle, if you consider a big chain, and if the Q2 units are at the middle, then what happens, it will be shielded quite a lot. But once the Q2 groups start coming close to the terminal Q1, then what happens, there can be a change in the bond order in the bond, and in fact a bond order can increase, and as a result of this you get a slightly positive chemical shift. That is why we get a slight positive shift. These are minor things, additional information which we are getting. So if you see the center of this peak is coming slightly, means frequency or the chemical shift is slightly in the higher side. Here it is coming around minus 16 or 17. Here it is coming around minus 14 or 15. So this also indicates that toward the end, Q2 units, toward the end of the ring it is approaching. Q2 units are coming. And this peak is characteristic of that. So that is why, since they are close to that, then you will get also a Q2 to Q1. That transport, that magnetization exchange is also possible. So let us move further. That is what I think I have mentioned here. This I have anyway, I have mentioned the last class also. Q2 is the ortho peak or the diagonal peak dominance. This I have explained the last class. Now this is the, so what are the possible structures? One is this long chain structure, presence of linear chains. Then this type of structures are possible. But this type of structures, there is no networking. You see, only one bridging oxygen is there. So this cannot form a long network. So this will make glass a little bit unstable, because what happens, this bridging oxygen is okay, charge is neutral, but the remaining all have this negative charges, because there is only one bond. So the another negative charge should be neutralized by sodium ion or protons. So this is not a good situation, because the moment you put this glass in water, normally sodium ion undergo exchange, or sodium can be replaced by hydrogen or H+. So this type of exchange take place. In addition to that, this also deteriorates the glass property. So this type of long chains are always good. If you can get it, is well and good. But if you have more Q1, suppose you have a glass of only Q1, then definitely we have this type of structural unit. Suppose you assume that you only got Q3, so only Q2 structural unit, there is no Q1. Then we have this type of ring possible, correct? Na? Why the ring is possible? Because there is a phosphorus here with the 2 bridging and the 2 non-bridging. So they formed a ring. So there is no Q1 structural unit. So only a Q2 structural unit is presented. So what is predicted for this glass, or what is from the calculations, and also this has been supported, that mostly this type of glass, which is nothing but 58% Na2O and 42% P2O5, contain this type of linear chains, along with some ring structured. This can be a 3-membered ring, 1, 2, 3 phosphorus linkage, or it can be 4 or 5 or 6-membered ring without any Q1. So these two are the 2 probable structures predicted. But among them, this is having the more probability, because this is a linear chain is found to have a more probability. This also has been supported by many theoretical calculations and ab initio calculations. So information regarding the structural phosphate we can get. That is what the NMR says. See, linear chains of Q2 groups with the Q1 end groups. That is what I am saying here. Linear chains of Q2 structural unit with the Q1 end groups. Then diphosphate groups. What are the diphosphate group? This is a diphosphate group, and this is a cyclic phosphate group. So these are the common structures present in many of the binary phosphate classes. particularly for some composition of this type of composition, maybe around sodium oxide 50 to 60%, and phosphorus maybe around 50 to 40%. This type of structural units are present. So what happens when you increase the concentration of sodium oxide? This is something chemistry can do, and or a chemist can do, and that is also reflected in the NMR pattern. The moment you add sodium oxide, what happens? The bridging oxygens keep on getting converted to non-bridging oxygen, and the chain will keep on decreasing, and a stage will come, you will end up with this type of structural unit. That is what I want to convey from here. If you keep on increasing sodium oxide, the chain length will keep on decreasing, and a stage will come, you will get this type of structural unit wherein we have only Q1 structural unit and we will not get any Q2, and accordingly the glass properties will change. So this we call as a network modifying action. We will not go into all the details. Let us go further. What additional information? Additional information just now I have mentioned, I am repeating for your sake now. The mean isotropic chemical shift to the Q2 groups giving rise to Q1 cross peak. You see here, see this is the spectrum, two-dimensional spectrum. This is the 2-1 peak. 2-1 peak because of the Q2 to Q1 magnetization transfer. Its chemical shift is slightly positive compared to the main Q2. So this is because the moment, as I mentioned, the moment they come towards the end group, then the chemical shift increases. So this is a very interesting observation. Why the chemical shift increases the moment in Q2 from the middle group, or the Q2 at the middle of the chain becomes Q2 at the end of the chain. See, for example, this Q2 is at the middle. Of course, here only 4 are there. But if you very big number, when the n is a very big number, I forgot to write n here. Let me write the n so that you will not mistake. This is n. So at the middle, there is a middle Q2 structural unit. And towards the end, for example, somewhere here if you see, or somewhere here, towards the end of the chain, you cannot be, Q2 cannot be at the exact end of the chain, because at the last, at the fag end of the chain, we should have only Q1. So Q2 may be in between the Q1 and the Q2. So if the Q2 structural units are coming towards the end of the chain, what happens? There's a chemical shift increase, means shielding decreases. So that is why you see there's a shift, systematic shift of around 2 to 3 ppm when you go from a Q2 at the middle and Q2 at the end. Q2 at the middle of the chain are more shielded compared to Q2 near the end, or the Q2s which are closer to Q1. Q2s closer to Q1. That is very important aspect. Q2 closer to Q1. They are very much de-shielded. What is the reason? Probably, if you have listened or if you have come across our previous lectures, or in the first 3-4 lectures, I have mentioned that the shielding is normally given by a parameter called sigma, shielding constant, etc. Consists of 3 terms. One is called diamagnetic term, another is the paramagnetic term, and the third one is nothing but the fluctuating electric fields. That is can be coming from the benzene ring, or from fluctuating fields can be there whenever this ring currents and all those things give fluctuating contribution to the shielding. But the fluctuating contribution in our case is negligible, because we are not considering any aromatic ring current and all those things. It's a purely inorganic system, and we are considering phosphate tetrahedra, in which phosphorus is coordinated with 4 oxygen, and the electron bonds are oxygen, phosphorus. There is a delocalization of the electrons. There is a single bond character as well as a double bond character to the phosphorus oxygen linkages. And in such cases, the sigma star and the sigma local dia, you can be, there won't be any change, because they are constant, because always say near neighbors are oxygen, and also PO4 tetrahedra angle is remaining more or less same. So sigma star is also same. So the contribution which makes a significant extent to the chemical shielding is nothing but the paramagnetic contribution. So paramagnetic contribution, it depends on a parameter called bond order in PO linkages. Bond order. We know bond order is nothing but the double bond is having a more bond order compared to the triple bond. Triple bond is having a more bond order is higher compared to double bond. Double bond is in turn having a more bond order compared to single bond, etc. This you must be knowing. So whenever there is a PU bond order increase, or whenever there is a free electron density more in the bonds, then we get a slight negative contribution. You see, this terminology is negative. And this formula is for diamagnetic contribution which is remaining same only, which we will not be considering, and this is due to McConnell's equation. There's one more McConnell's equation which will not in ESR which we will not discuss. So this is related to the work, something which is derived by McConnell. The sigma local paramagnetic is given by this expression. Here the parameters are more or less same. Only the parameter which changes is nothing but the bond order. So bond order of the PO changes when you come from the middle of the chain towards the end. Because in end what happened Q1, lot of delocalization is there. The negative charge get delocalized completely, the bond order is higher. So its chemical shift value also higher. But when Q2 structural unit come close to the end members or end groups or near the end of the chain, then we will have a more delocalization. So bond order slightly increases, and that is the reason that we get a negative value of sigma increases. The moment the negative value of sigma increases, sigma total shielding decreases, and we see a slight increase in the chemical shift values. This has been confirmed by various experiments, also theoretical calculations also. So the whatever contribution coming from a bulk Q2 or a Q2 species which is in the bulk of the chain shifts toward the end is all because of the change in the electron density of the PO bonds. So hope these things are clear to you. These are very important informations. In fact, you can also support this with the help of an vibration techniques, etc. Let us move further. So last class I have discussed a composition called G58. What is G58? 58% sodium and 42% phosphate. Now I am discussing another composition, how the NMR spectrum changes. You compare this spectrum with that spectrum. So this NMR glass is having a composition of 35% P2O5. Sorry, 35% sodium oxide and 65% P2O5. The previous one which we have studied, this we called as G35. The previous call we call as G58. What is G58? G58 is but 58% sodium oxide. Here the composition has changed. It has become 35% sodium oxide. So just to see, in fact, I did not plot it simultaneously together, but you see, always you can always refer the previous NMR spectrum. For example, this you can always see in your previous lectures or in your notebook. This spectrum and this spectrum, you see how much difference is there. You see, you can see one thing. You can see there's a broad peak which is coming. Correct, na? So this is not a well-resolved peak. Whereas in the first case, you got a well-resolved peak. But there you have also got well-resolved peak for Q1 and Q2. But here what happened? We have got different structural units. There we have got two peaks. If you remember correctly, or for your information, I will tell you, we have got two peaks. One is around 0 ppm and another is around minus 20 ppm. Is it now? And the Q1, that is characteristic of the Q1, 0 ppm correspond to Q1 structural unit and 20 ppm corresponding to Q2 structural unit. Whereas Q1 means only one bridging and the Q2 means two bridging. Whereas the moment you decrease the concentration of sodium oxide, sorry, increase the concentration. No, I have made a mistake. For example, yes, you are right. This is 35%, means you are decreasing the concentration of the sodium oxide. In previous case, you are increasing the concentration, 58%. Now you have only 35% only sodium oxide concentration. So what is happening here? Q2 and Q3 are coming at a much different value. Q2 is coming at minus 20 ppm. There also it came at minus 20 ppm. The same Q2 structural unit only is here also it is present. But instead of minus 20 ppm, we have an additional peak around minus 40 ppm. You see here minus 40 ppm Q3. This is nothing but the Q3 structural unit. And from 1D NMR, you can fit and find out also how much Q2 is there and how much Q3 is there. What is Q3? Q3 probably you must be knowing. Q3 is nothing but phosphorus structural unit, 3 bridging oxygen atoms. Correct, na? Probably I will have a structure here. I will come back to this point later, but for showing you Q3, what is Q3? You see here phosphorus here, one double bonded oxygen, and 1, 2, 3, 3 bridging oxygen. Correct, na? So 1, 2, 3, 3 bridging oxygen, because these oxygen bridges to phosphorus structural unit. So we have a Q3 structural unit here. Correct, now this is C3 bridging oxygen, and one is non-bridging or one is a double bond. In fact, there will be a delocalization must be happening in all these bonds, but bridging is only 3 and one oxygen is a terminal oxygen. So this is a Q3 structural unit, whereas this one, this phosphorus which I am showing the mouse now is nothing but Q2 structural unit because 2 bridging is there. Now go back to your NMR spectrum once again. So you understood what is Q2 and what is Q3. Correct na? Q2 is understood, what is Q3 you understood. But one thing we are happening here, this is the one dimensional NMR in the single quantum and this is nothing but in the double quantum. You see here 3, 3. The broad peak is because of 3, 3. You see here 3, 3 means what? Magnetization is getting exchanged from Q3 to Q3 itself. So Q3 and Q3 are dipolar coupled. In other words, Q3 forms an extended network. There is no Q1. There is no terminal groups here. You see here terminal groups are not there. Q1 groups are not there. So these are mainly nothing but the chains. If you have a linear chain, what happens? We should have Q1 and Q2. Is it not? If you want a, because some terminal group we want, if it is a linear chain. So here there is no linear chain. Linear phosphate chains are not there in this class. Very important information. Here, many times what we observed is either a chains, rings of P2, Q2 and Q1, Q2 and Q3, or Q3 rings and Q2 rings can be possible. So let us move further and let us see what information you can get from this pattern. Okay, what the inferences we can draw. Since I have shown an NMR spectrum, so what are the inferences which we can draw from this NMR spectrum? So as I mentioned, this contains only 35% sodium oxide, and from the just one dimensional NMR, I have calculated or evaluated how much is Q2 and how much is Q3. So Q3 is relatively less, Q2 is more. Whereas in the previous case you see Q2 is very high, 62%, and the Q1 is very small, 38%, relatively small. Here you can say more or less same only. One is 45 and another 50. If you increase 5%, this becomes 50, and if you decrease 5, it becomes 50. So Q2 and Q3 are more or less same, I should say. Of course, if you see the NMR pattern also, they are only marginally different. Let us move further. What are the inferences? You see considerable spread in Q3 chemical shift value. Now I am asking you why. You see the this is significantly spread Q3 value. Why? The line width is larger. Probably last class also I have mentioned, when you have a Q3 structural unit will be bound by 3 bonding of this nature. Suppose I am bound by 3 people, then as a person I cannot move here and there. Suppose one person goes away. If I am bound by 2 people, then I have got little bit freedom. Suppose I got only one more person go away, then only one person only is pulling, then my freedom increases. Freedom of movement increases. Here also the same thing. The Q3 is bound in all the 3 sides by the phosphorus structural units. So its movement is less. It is free rotation is very, very less. It's a rigid system. So whenever we have a rigid system, and in glasses what happens, we have a distribution in bond angles and bond length, and the free rotation is not allowed. Normally the line gets broadened. Whereas Q2, you see, the line is relatively less sharper, means relatively less broad, you can see here. So Q2 is less rigid compared to Q3. That is an important aspect which I thought I will mention to you. Then another aspect is that Q3 and Q2 are overlapping. When this happens, because Q3 is a more disordered system, because there will be a distribution in the bond angle, bond length, because it is bound by 3 directions. So it is a slightly disordered system. Everybody will pull, or every direction there will be pulling, and it takes a compromising situation. The phosphorus in Q3 structural units take a compromising situation, and it got slightly distorted. That is why there is a bond angle distribution, bond length distribution, etc. And as a result, you get a broad Q3 peak. And it indicates that the disorder is more. So Q3 is more disordered compared to Q2. The moment you add sodium oxide, what happens? It will try to attack this bridging oxygen atom, breaks the bridging oxygen atom, disordered structure will go away, and we will get more ordered structure. That is why there is a network depolymerization takes place by adding sodium oxide. Disordered structure become more ordered, Q3 become Q2, and more ordering will happen. Another important aspect is that when Q3 become Q2, what happens? The non-bridging oxygen concentration increases. Is it not? Non-bridging oxygen concentration increases. If you make an analogy with the crystals. Always we make, normally the spectra and all, we make an analogy. Suppose I got a spectrum for this compound, I then try to correlate with a similar compound which gives a similar spectrum. Then I get some information regarding this unknown compound. So what is happening when a Q3 is getting converted to Q2? You generate a lot of non-bridging oxygen atom. Okay. Normally in solids, if you consider in any of the solid, oxygen forms the valence band. Is it not? In many of the solid, if you take zinc oxide, tin oxide, gallium oxide, sodium oxide, any oxide if you take, oxygen orbitals are forming the valence band and metal orbitals are forming the conduction band. Is it not? That is the general convention. In any metal oxides, metal forms the conduction band and oxygen forms the valence band. Now, you are doing one thing. You are creating additional negative charge to oxygen by adding sodium oxide or you converting Q3 to Q2. So once negative charge excess comes to the oxygen, what happens? The electrons from oxygen or from the valence band can be excited to the conduction band easily without much trouble. So with the lower energy itself, because negative charge is coming to the oxygen. So once negative charge comes to the oxygen, oxygen is having a rich electrons, correct? Now oxygen is rich in electrons. That electrons or the lone pair of electrons, etc., can be easily excited to the higher level. So as a result of this, you see a band gap, or no, I should not say band gap, optical gap decreases if you increase Q2 at the expense of Q3 structural unit. So this Q3 to Q2 conversion can also be followed by just taking UV visible optical absorption spectrum. But of course, you will not get the relative concentration of Q3 and Q2 in UV visible optical absorption, but you can always explain the shift in the onset of wavelength of absorption by conversion of Q3 to Q2 structural units. So this property is used for making band pass filters, etc., for different applications. So coming back to our NMR spectrum once again, spectrum in DQ dimensions are poorly resolved. That means there is an exchange taking place. They are strongly dipolar coupled. So exchange is taking place significantly between Q1 and Q2 structural units. The dominant connectivity is found between Q2 and Q3 groups. That is also correct. Dominant, that is why we see there is no resolved peak. We see a lot of Q3, 3-2, 2-3 peak and 3-2 peak, and 3-3 peak also quite intense. So what additional, this is some of the inference which we have got. It is not giving a very clear-cut picture compared to the 58% sodium oxide. The main reason being that resolution is poor. You need to go for a higher spinning frequency, etc. This probably we will discuss maybe towards the next class or maybe in the last class. What additional information we can get? Auto peak. Q2 auto peak. Q2 groups connected to Q2 groups. So auto peaks also there. You can say the auto peak. Auto peak means diagonal peak, which can say 2-2. So 2-2 linkages are also there. Of course, in intensity somewhat smaller, but predominantly Q2 is Q3 is there. Q3 exchange is more predominant, but some Q2 structural units are also there. You can see from here intensity is slightly poor. So 2-2 auto peak is there. So 2-2 auto peak is possible only if we have this type of ring type of structures. Correct now? Ring type of structure of only Q2. Then only the Q2 can exchange the magnetization. So definitely this type of ring type of phosphate structures are there in this combo, in this type of glass composition. Then another possibility is that this type of structures, you see here, the phosphorus is here in Q3 structural unit and they are connected to, see, another phosphorus with Q2 structural unit. And this Q2 is connected to another Q3. So you have a Q3, Q2 and Q3. This type of structure is also predicted, but in that case, what will happen? Q2, Q2 exchange will be less. Q3, Q3 exchange also will be less. Correct now? Because in between there is a structural unit present. So due to that, we could not get much information from this spectrum, but from the 2D spectrum, one can always say there's a good interaction between Q3 structural unit because there is a magnetic exchange taking place between the significant extent of magnetic exchange taking place between the 3-3 structural units and 3-2 structural units. And 2-3 also there, as you can see from the intensity. So this much information only we could get. The main reason for this composition is that the peaks are slightly unresolved. That is why we could not get much more information like in the case of the previous case. Previous case we could get good information. Is it not? So these are the possible structures, mainly present in this type of composition. So as you keep on increasing pure P2O5 glass, if you take now, you will see mostly Q3 only. Pure P2O5. This is anyway 35% sodium oxide. If you don't have any sodium oxide, then we will not see any non-bridging oxygen atom, and we will see a network, distorted network of P2O5, in which we get only a broad Q3 peak. Let us move further. This diagonal peaks, which off diagonal peaks, if you say off diagonal peaks, if you measure the intensity, you can always calculate the distance between Q2 or the distance between the Q2 and Q1 structural units in glasses. So that is related to dipole-dipole coupling also, but that alone will not do, but this has to be confirmed with some ab initio calculations also, so that this is then only we can predict the geometry. The distance information we will get from the distance information alone, you may not be able to predict the geometry. We need to support it from theoretical, this one. So normally when you do, people do solid state NMR, they will always, there's a person who theoretically also predict, okay, this type of structural configurations are possible, energetically feasible. So then they correlate their results with the experimentally observed pattern. So both theory and experiment go hand in hand. Of course, simple things we can predict, a Q1, Q2, a stage, what is the type of the structural unit present, etc. we can predict. But if you want to evaluate the distance between the atoms or distance between the groups, etc., you need to have some sort of a simulation program also along with this. So one more example I will explain, give regarding this double quantum. It's a double quantum NMR is very widely used, a very simple technique and very widely used to identify the structures, particularly in crystalline compounds, because many times now if you do for high power experiment, high power NMR experiments like multi-quantum, etc., many times standard NMR probes cannot do. We require, I think, high power amplifiers and high power probes, etc. Whereas the double quantum NMR can be done in any NMR machine. We can do this type of double quantum experiment, and it gives without any problem or with quite conveniently, or you can very easily interpret the results without much difficulty. So let us take a compound called magnesium phosphate. Magnesium phosphate crystallizes in two modifications, alpha form and beta form. You may be knowing many of the inorganic compounds crystallizes in multiple forms, we call it as allotropes. Sulfur is having many allotropes. Quartz is having different allotropes, alpha quartz, beta quartz. Alumina is also having different material, different isomorphs. Sometimes we have alpha alumina, sometimes we have gamma alumina. Of course, we will discuss all those things probably maybe tomorrow or Monday. So this type of allotropes are possible. A similar type of allotropes also exist in the case of similar type of allotropes also exist in the case of magnesium phosphate. So this is a typical magnesium phosphate is a pyrophosphate. If you know what is pyrophosphate, pyrophosphate is nothing but two phosphorus structural units are there. This type of linkage as well, POP, correct? Na? Then we have this shape, O, 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 O minus, O minus, O minus, O minus. How many oxygens are there? 1, 2, 3, 4, 5, 6, 7. 7 oxygens, correct? Na? So this double, sorry, this is not a single bond, this is a double bond. So P double bond oxygen is there, O minus is there, O minus is there. 4 non-bridging oxygen atoms you can say. So this we can always say this like a Q2 structural unit. This is not Q2 structural unit, Q1 structural unit. Why Q1 structural unit? Because we have only one bridging oxygen. So this cannot be a Q2 structural unit. This is a Q1 structural unit. Is it clear? So there are two Q1 structural units are existing. But these two Q1 structural units are different, particularly for the beta magnesium phosphate. I think I should make a correction here. So what happens? Alpha and beta forms of Mg2P2O7, correct? Na? Alpha and beta forms of Mg2P2O7 are existing in this sample. Only thing is the alpha form is relatively less amount compared to the beta form. So in the beta form, what happened? Na? Beta form, there are two types of phosphorus structure loaded. Whereas alpha form, we have only one phosphorus structure loaded. That is why we are writing here, this is the alpha form, the CP, which corresponds to phosphorus 31 is nothing but the alpha form of Mg2P2O7, and beta form is having two peaks, which are represented by A and B. What do you mean by two peaks? Two peaks means there are crystallographically two different phosphorus which are existing. The only difference is nothing but slight change in the bond lengths and bond angles. One phosphorus is having a slightly different bond angles and bond length compared to the another phosphate structure unit. So that is why two type of phosphorus structure units are existing. So that is very clearly seen in the case of a one-dimensional NMR also. What is the equal percent? One phosphorus structure unit is characterized by A and another phosphorus, crystallographically different phosphorus structure unit is characterized by B. So one is more shielded and another is less shielded. The C peak is nothing but a small amount. Normally, if you prepare beta, a small amount of alpha also remains. So that is why, because sometimes this comes as an impurity. Once you convert alpha to beta, then only alpha form get converted to beta by suitable treatment, temperature treatment, etc. So sometimes what happens, part of the alpha phase also remain along with the beta phase. That is why we see a P because of this alpha group. So A and B are for beta Mg2P2O7 and the C peak is because of the alpha. So this is a very clear picture, very simple NMR spectrum which anybody can interpret without much experience in solid state NMR. But if you do a DQ NMR, what happens? You see A peak is here, B peak is here. BB interaction is taking place. Is it not? BB coupling is taking place. B and B are interacting each other. So BB coupling is taking place. And AA coupling is also taking place. You can see double quantum signal of A is seen. But one more thing you monitor, as I mentioned here, the intensity of the cross peaks. You know, cross peaks, off diagonal peaks, not diagonal peaks, off diagonal peaks. You see, their area is higher compared to this peak. What does it mean? This means that there is a magnetization exchange taking place between A and B. There's a magnetization exchange taking place between A and B. A and B here, A to A here, A to B here, B to A here. Is it not? B to A here and A to B here. And their chemical shift also nearly equal. But if you see C, there is no exchange possible because C is present as a separate phase. C is a separate phase, correct? Na? Separate alpha Mg2O7 phase. It is not interacting. It is only physically mixed. It is not interacting with the beta form of Mg2P2O7. It is only physically mixed. So there is no magnetization exchange between B phosphorus or A phosphorus with the C phosphorus. That is why we don't see a cross peak or an off diagonal peak corresponding to C. Off diagonal peaks only you can see for the B and A phosphorus. A phosphorus also you can see, B phosphorus also you can see. So there's a significant extent. So many times you get a mixture. When you isolate a natural compound or a natural phosphate from underground, many times the cyanotimes, etc. Now, cyanotimes, then different types of phosphates are there below the earth. So people do this once they underground, once they do dig the earth, then what happens? They get this type of phosphates. So they get this type of phosphate. So you will get normally not a single component. You will always get a mixture. Pyrophosphate you will get, orthophosphate you will get. So by doing a 2D NMR or this double quantum NMR, you can see whether it's a mixture or whether it's a crystallographically different phosphorosity. Had it been a crystallographically different, we would have got a cross peak also here corresponding to C. We don't get that. So it shows that C is nothing but a separate phase. And A and B are nothing but the single crystal structure in the two different types of phosphorus. So not the higher intensity of the cross peak compared to AA or BB peak. That shows the effective magnetic interaction taking place between the two phosphorus. Hope things are clear to you. So and another thing also you may note here. So you see the 1D spectrum. You see 1D spectrum. You can see only two peaks. Sorry, three peaks. 1, 2, 3. Two peaks for one peak for A, one peak for B, and one peak for C. But in double quantum side, you see 1, 2, 3, 4. One additional peak has come. Why this additional peak has come? This additional peak has come because of the magnetization exchange between the two phosphorus structural unit present in beta magnesium phosphate. Hope things are clear to you. So cancel, na? Not moving. What happened? Yes, sorry. Sometime. So similar to this 2D, this DQ mass NMR, na, actually slightly or comparable version you can say. It is also same information it gives. This double quantum, instead of double quantum, sometimes you see they do the exchange of magnetization also can be monitored with the help of a suitable pulse, 180-degree pulse. So this is called a direct detection of connectivities in glasses by 2D exchange. Let me close this so that it will be clear to you. So 2D exchange NMR, 2D exchange. Exchange is nothing but not proton exchange or isotope exchange. It is a magnetization exchange. Magnetization exchange can be also monitored by applying certain pulse sequences. So there, in the previous case, I told two-dimensional double quantum by giving the pulse high power pulse, and you create a double quantum, and then you can one axis you monitor double quantum, and another axis you monitor single quantum. Here what happened? Here there is a mixing time is involved. These are all pulse separate pulse sequences are available with the 90-degree pulses and 180-degree. This is a 180-degree pulse. So that can be correlated with the rotor period. This is called a rotor. This is nothing but a rotor synchronized pulse programming. Rotor. According to the rotor speed, you synchronize the pulses. And here you apply a pi by 2, another pi by 2, and then a 180-degree, and this is nothing but the signal. Correct, na? So this is nothing but the whatever pi 180-degree, 90-degree pulse you apply to monitor the signal. If you remember the old in the last class I have mentioned how to record. Single pulse is not possible to record a 2D experiment. Correct, na? We need to have multiple pulses. Minimum 2 pulses are required. One is nothing but the preparation period, then evolution period, then acquisition period. Hope you remember. I think I will not go to that bit, but you go through that in your room and or in your after the class, and we can discuss it maybe next class or next class. So minimum 2 pulses are required to do a 2-dimensional NMR spectrum, to record a 2-dimensional NMR spectrum. So here, in addition to actually we are applying almost like multiple pulses. 190-degree pulse is applied. Again, one more pulse we apply to remove the transverse magnetization, and another we apply in a 180-degree pulse. This 180-degree pulse is applied mainly for magnetic exchange. You can, if those who are interested, can read regarding the pulse programming, but we may not be of that much discussing regarding this. But remember that for magnetization exchange only we are applying this 180-degree pulse. Rest all is same as that of the previous experiment. Irradiation of 180-degree pulse in the middle of the single rotor period, because this is a single rotor period. So pulse in the single rotor period. So what does it do? So if you apply that 180-degree pulses now, because you are doing a process called magic angle spinning. Due to magic angle spinning, the dipole-dipole interactions gets averaged out. But so we say it is getting cancelled, it is getting decoupled. But by using 180-degree pulse, we can recouple this dipole-dipole interaction. That is what I am written here. The recoupling of the dipole interaction takes place. So once there is a dipole-dipole interaction, magnetization will exchange, and you can have a signal in both the x direction as both the x and y axis. That is what we see here. See, one axis is this one, which is nothing but the single pulse for one dimension. And this axis which you see here is nothing but which takes into consideration of that magnetic exchange. Correct? Now here, that is why there is no pulse applied. There is no 0 millisecond means there is no exchange pulse applied. So you will get only a diagonal peak. But as you keep on putting some mixing time, because there is a mixing, you are applying a pi pulse at some intervals. If you apply at interval of 0 millisecond, because there is no application of pulse, so you will not get a cross peaks. The moment you start applying pi pulses, the time delay, mixing time will come into picture. If you keep the mixing time 2.5 and you keep millisecond, if you keep the mixing time to 10 millisecond, then you see a significant change in the 2-dimensional NMR. So this is nothing but the single pulse And this dimension is obtained after applying 180-degree pulse. So you see how the line shape changes by changing the mixing time. Whenever t is equal to 0 means there is no 180-degree pulse. So the moment there is no 180-degree pulse, then you will get only a peak, single peak. The moment you start applying 180-degree applying pulse, you start generating mixing times, and once the mixing time increases, you can very, very clearly see the magnetization exchange taking place between the Q2 and Q3 groups. Q2 and Q3s are nothing but the two phosphorus structural units. You can, for the time being, you can consider like that. So exchange, 2D exchange also can give the same information, but if you see the double quantum is very more clear, is more advanced, because what happened, double quantum with the help of phase cycling, we can remove the unnecessary noises and we can get a good spectrum. For example, in the case of crystalline compound, you see how much resolved double quantum spectrum is. And for the another composition of the glass, which I have shown in the previous class, you can see a well resolved peak. So even though it is a glassy structure, you can see well resolved peaks in DQ mass NMR. So DQ mass NMR is a slightly higher version of exchange NMR. Although it gives the same information, the noises are relatively less. Only a small noise is lying here. Other than that, the noise is relatively clean spectrum we can get, because with the help of a phase cycling, we can remove a lot of noise in the case of double quantum. So people have modified, or people are now going for, instead of exchange NMR, people are going for this double quantum NMR to get better information. Of course, now more and more new techniques have come in which you can get a better information. So then double quantum NMR, that also will be discussed. So then now let us go further. So this I have 2D exchange is an alternative of 2D exchange is an alternative of double quantum, but double quantum is preferable or have more advantages compared to DQ, this exchange 2D exchange spectrum. So now let us give one more example of this 2D one-dimensional 2D experiments, and with that then I will move to something different. So I have today, just now I have told this dipole-dipole coupling can be generated with the help of pulse sequence, and this pulse sequence helps to get cross peaks, and from that you get information regarding the dipole coupling and distance dependence of the structural units, etc. So you can predict what is the type of structural unit present. And this is a very good gift, very big gift in glasses. What happens in glasses, we cannot do NMR or neutron diffraction or any other technique. Only this type of NMR technique only we can use to get this type of information. Now, let us do a slightly different experiment called correlation experiment. Like probably in solution stage, you might have studied heteronuclear correlation. Correct? Now, heteronuclear correlation. The short form or abbreviation for that is HCO. HCO. Correct? Now, then homonuclear correlation is also there. In proteins and other organic molecules, they will always try to correlate the proton NMR, proton signals. So that is a proton-proton HH correlation. Whereas HH correlation we cannot do here, because in solution state, people work, or mainly the NMR spectra are recorded based on the J coupling. You know, this we have discussed in the last class. So what is J coupling? J coupling is nothing but a scalar coupling or through bond coupling. Whereas here, that type of coupling is not there. We have a through space coupling. Dipole-dipole interaction is a through space coupling interaction. So through space is something very strong. It depends on the distance also. But that is why I am telling you that coupling constant of dipole-dipole interaction is of the order of few hundreds of hertz or kilohertz. Whereas the coupling constant of J coupling or the J coupling values are of the order of few hertz. So people, I think nowadays anybody who works on material science, they try to work on graphene, because graphene is considered to be a novel material. And a lot of work is going on, and a lot of research people are doing. It is used as an electrode, it is used as a two-dimensional materials, etc. Coolant materials, or many applications people are saying, hydrogen storage, etc. So the graphene, normally, how people make graphene? Graphene is nothing but a graphite, single layer of graphite only. But people start from graphite and then convert it to graphene oxide. And then graphene oxide is nothing but related to graphene, because surface you have a lot of carboxyl groups, hydroxyl groups, etc. So it is somewhat insulator or a semiconducting type of material, whether a graphite and a graphene are nothing but conducting material. So you see here, if you make a graphene oxide by Hammer's method, which is a well-known method, you will get a lot of COH groups here. You will get a COC. COC is what? Epoxy linkages. Epoxy linkages. This is nothing but not phenolic linkages, I should say. It is nothing but an alcoholic linkages, correct? Na? Methanolic linkages or ethanolic linkages. And this is nothing but the main species, which is nothing but the sp2 carbon. Graphite, we have sp2 carbon, and graphene also we have sp2 carbon. But graphene oxide, we have sp3 carbon also, we have sp2 carbon also there. Correct? Na? So that is what we see here. You see here, we have an epoxy carbon, we have a hydroxy carbon, and we have also a sp2 carbon. If you take an one-dimensional NMR, we don't know what is happening. Is there any communication? Is there a magnetic exchange between sp2 carbon and whether an COH group and this epoxy carbon or hydroxy carbon? Is there any communication between sp2 carbon and hydroxy carbon or methoxy carbon or epoxy carbon? We do not know. You see the spectrum, we cannot say anything. But if you go for a two-dimensional NMR spectrum, if you go for a two-dimensional NMR spectrum, that is called a C13 correlation spectrum. Correct? Na? I am trying to do a correlation. I am not doing a double quantum NMR and all those things. I am doing a correlation. I wanted to see, I want to correlate one peak with respect to the other carbon. I want to correlate one carbon with respect to the other carbon. So here we do a C13 correlation spectrum. See, you cannot do a correlation spectrum simply because, first of all, unlike phosphorus, C13 abundance is very, very small. So we need to enrich the sample. Carbon 13 has to be enriched. In addition to that, we need to do a CP mass. So a lot of pulses are applied. You see, CP mass itself, you know how many pulses are applied. We have a contact pulse, we have a 90-degree pulse, we have a decoupling pulse in proton channel, and then we have an X-nucleus pulse. In addition to that, we have to do also for this double 2D NMR pulses. So this is somewhat pulse-rich NMR spectra, as NMR spectroscopy. So here we do a C13 correlation spectra. One C13 we are correlating with the other C13. So he combined two things, two experiments. One is CP mass. What is CP? CP stands for cross polarization, and mass stands for magical spinning. So we do cross polarization, and that too enriching the sample with C13, because we are studying C13 coupled. So their abundance is small. So if sufficient amount is there, then only we can get C13 exchange. So that is what we are doing here. And here we use a separate pulse sequence, which is comparable to that only, but slightly modified modern pulse sequence called RFDR. It's a modern pulse sequence, RFDR, very powerful pulse sequence that is called a radio frequency dipolar recoupling. This pulse is called a radio frequency. I have not written. If you see in Google, you can see radio frequency dipolar recoupling. Radio frequency dipolar recoupling. This is a pulse sequence. You see, recoupling sequence, not decoupling, recoupling. You want to recouple, now you don't want to recouple. If you do decouple, then you will not get information. Of course, the line will be broad, narrow, but chemical this space information or the connectivity you cannot get. Or the physical phenomena like magnetization exchange or the population exchange you cannot see. So for that, we need a technique called RFDR, radio frequency dipolar recoupling. And this recouples the dipole-dipole interaction, and in addition to the diagonal peaks, you see here, these are the diagonal peaks. This diagonal peak is corresponding to it overlaps because there is a COH group, hydroxy carbon as well as a epoxy carbon. And there is a sp2 carbon. sp2 carbon is, you see here, there is less intense, whereas this is more intense. But an interesting thing is that, you see the epoxide peak is correlated to the sp2 peak. Correct? Na? Epoxide peak or the hydroxy peak is correlated to the sp2 peak. Similarly, the sp2 peak, correct, now also correlated to the epoxy peak or hydroxy group. There's a small unit here that is appearing as here, this small structural unit. Forget about that for the time being. So this may be some CH linkages, etc., or CH2 type of linkages taking place. But if you see here, there's a communication or there's a magnetic exchange taking place between sp2 carbon and epoxy and hydroxy carbon. It's a very interesting information for because many times people use for magnetic applications, also magnetic shielding, etc. So this magnetization change is a new information with graphene oxide. So probably for the time being, I will stop for the 2D NMR. Then we will go for a taking maybe another one slide. I will explain to you on 1 or 2 slides, and then I will stop. Maybe 2-3 minutes I will take, and then I will finish. One important experiments called the spin echo experiments. Spin echo experiments. What is spin echo experiment? Echo always we know. Somehow, suppose I say something, my voice will go somewhere and then comes back. Is it not? So it will hit somewhere wall or some very big rock and then comes back. We call it an echo. So like the same terminology is applied here. Why we apply here? Because you see here, the moment I apply a 90-degree pulse, correct now? The moment I apply a 90-degree pulse, magnetization, I am applying pulse along y-axis, correct now? And already the magnetization is along the z axis. So two forces are there, y and z. So these are two vectors. So resultant will be the cross product of y and z, and you get a mutually perpendicular direction magnetization. So by applying a 90-degree pulse, you bring the magnetization to the x-axis. But the magnetization, the moment it comes to the x-axis now, they start spreading. You see here, they start spreading. Because there is nobody to hold it, first of all. And pulse means we apply for short time only, it will be not there. Now, it will start fanning out. This is called spreading or fanning out. I think I have explained you also sometime in the beginning, but just for your refreshing your memory. So it starts fanning out, and if you apply a 180-degree pulse, what happens is gas start getting focused. In other words, the magnetization starts getting defocused initially, and after some time, if you apply a pi degree or 180-degree pulse, it starts getting refocused. Is it is it clear to you? See, I bring the magnetization 90-degree, apply a 90-degree pulse, magnetization come to x-axis, it starts spreading or it starts defocusing. Better word is defocusing. And by applying application of a 90-degree pulse, you start refocusing the magnetization, and finally the refocused magnetization will appear as a strong signal. Initially people were doing this. Why people were doing this? Because initially dead time problems are there. See, the detector will not respond immediately. The electronics will have a dead time. They will not immediately, 0 time, nobody can detect the signal. There will be always a delta t, time involved in the signal, monitoring the signal. So dead time problems are there. So dead time problems can be avoided. How you can avoid it? By you doing this, because by you apply a pi pulse, correct now, you apply a pi pulse, then the whatever magnetization which are defocused will start refocusing. And in this process, you will get some time. You will get some time for saving. You will save time, and you can get the signal very efficiently. Just I thought I will show you, because what we measure in NMR is nothing but a decaying signal. Correct now, a magnetization will be decaying inside a coil. The moment a magnetization decaying inside a coil, it will produce a decaying current, and that is a signal in NMR. So that is why we can measure the decay like this procedure. Because we see the decay at t is equal to 0 sign, coil will not respond. So for that reason only, we have introduced this spin echo experiment. But spin echo experiment can give valuable information regarding the structure. Probably I think I will stop here, and maybe in the next class I will give you an example how you can get using spin echo experiment to get information regarding the structural aspect. So please feel free to ask any questions or any clarifications. And probably next class also you can ask, and Monday also you can ask. Keep your questions ready. We will meet now only on Monday at 3:30. Oh, sorry. I'm sorry. We will meet on Friday. We will meet on Friday. I'm extremely sorry. We will meet on. Okay. Questions are there. Please. Yes. You are right. Very good. You are understood the problem. See, alpha form and beta forms, they are physically mixed. What happens when you make a beta form? What happens? Part of the unreacted alpha form also remains. So there is only a physical mixture. Nice question. Actually, it's a physical mixture. So whenever there is a physical mixture, the magnetization exchange will not take place. So that is why we don't see a cross peak. Off diagonal peak we don't see. Is it clear to you? Ranjan Sahu asked, I think. Go to that window. I don't know whether it is on. Thank you. Okay. Thank you very much for raising the question. So Friday we will meet. Sorry, I told Monday. Friday 3:30 we will meet. Friday is 28th July. At 28th we will meet. Please feel free to ask any questions. So any problems you try to answer. I have assignments. I have given a simple assignment only. Any doubts you have, we can discuss in next class or 11th lecture or 12th lecture. So now 2 more lectures are there. One is on Friday and another is on Monday. Friday we will meet. Friday 3:30 we will meet.
Yeah.
So shall I conclude this one lecture?
Go to the site. Any more questions?
Any more questions? Can we
At YouTube or some?
Tapas sir, please explain the phosphorus atom.
That question was already answered.
Answer.
Thank you, Tapas.
Thank you, Tapas. Thank you for raising the question. That means you understood. I am happy. Okay, thank you very much. See you on Friday.
Okay, thank you.
Thank you.